Okay, so we're talking about rotation. It's chapter 12. I'm just going to call it part 1. I don't know if we didn't end up getting through everything this class period for period 3. So let's first review all the different rotation terms that we've had to deal with and work with. First, in revisiting rotation in terms of how's rotation a vector, using all the right-hand rule stuff. Okay, so if you have axes in the x and y and z directions like this, and you have an object spinning so that it's spinning about the z-axis, if it spins in a counterclockwise direction, we would say that's in the positive z direction. We could represent the angular velocity vector with its magnitude and direction in this direction z. If it's in a counterclockwise, or sorry, it's in the clockwise direction, that's negative. So usually it's like that, right? Anyway. Okay, so just going down the list of different variables that we have. We talk about theta, which is our angular position. We have angular velocity, angular acceleration. Just remember when you write these, this is not just a W. You really, to distinguish it from a regular W, I really kind of curl the tips, kind of curl them in a little extra. If you want to think of it as like the first part of the Batman symbol. No? You see that? Maybe not. All right. So, just curl the tips. Angular velocity, and then you have angular acceleration. And so same thing with alpha. You make sure you have the extended. You just don't want it to be ambiguous whether you're writing W for like work or A for translational acceleration, and then angular acceleration and angular velocity. Make sure you're familiar with radians, degrees, and revolutions. Those are usually the units of rotation. And then we had the kind of connections between a spinning object and a circle, and its tangential components, or kind of its translational components with its angular components. Right? So we talk about tangential acceleration and tangential velocity, so on and so forth. Usually I just call this arc length. I guess you could call it a tangential position, but that's kind of weird. I haven't really seen that one as much. And then we also talk about radial acceleration or centripetal acceleration. Right. Just putting all the terms out there. We also talk about torque. Okay, so torque is like a twisting. If a force is a push or a pull, then a torque is like a twist. Okay. Now a couple new ones we're going to add on is I, capital I, for moment of inertia, or rotational inertia. I think on the AP exam I usually see it more as rotational inertia, but it's the same idea. Okay. And then we're going to add to it a rotational kinetic energy. We'll see that you can split kinetic energy up. Now a lot of this, rotation comes in when everything that we've done in translation, so like the boxes, or like sliding on a ramp, or the skier with rocket jet skis, whatever, we usually consider them like particles with no volume. Right? We don't usually take into account its volume, how tall the person is, how, its shape. None of that usually matters. Rotation always comes in when you start looking at rigid bodies with volume, right? Because now you have to look at how the forces are pushing in not collinearly, they're like offset from each other, and it tends to cause it to rotate. So kind of the same thing, you don't really have rotational kinetic energy unless you're taking into account an object with volume, a rigid body. Okay, so if we list out how they parallel from linear to rotational, R is like a theta. Like if I were, the College Board sometimes likes to throw these questions in there, you know, the analogs, right, the analogies so R is like, or sorry, theta is a rotational analog of position, or R, and then omega is like a V, alpha is like an A. So with these, you know, these are the rotational parts. Within circular motion itself, you had this connection between tangential and angular values. Don't worry about this thing on the side yet. Just ignore that. We'll come back to this one. Okay. So you got the circular stuff. And again, this only works for circular motion in that your motion needs to be perpendicular to your radius. Later on, when we get to orbits or gravitation, you know, orbits are elliptical, so sometimes your velocity goes away from the center and you increase your radius a little bit. Sometimes your velocity goes in towards the center, which decreases your radius a bit, and then this stuff doesn't quite work. Or we have to modify it a bit. Okay. We also had this one, right? The radial, the centripetal acceleration. This is always true, the VT squared over R. You kind of have to be careful about turning it into omega squared R. Just be careful of the units. Something that came up is how you get radians here, but this doesn't have radians in it. Radians is kind of a dimensionless unit. It's not really a dimension the same way meters and feet and joules are. So be careful about that. Okay, and then now we're adding some new ones. Okay, so if Newton's second law for translation is F equals ma, then we now have kind of a rotational version. Sorry, I crossed some stuff out. This is meant to be a star. I'm starring the things that are new. So the sum of my torque, and to be specific, this is the sum of my torque around a specific point, right? A pivot. Should equal to the sum of the forces from that pivot, how far away they are, that cross product, right? Keeping track of angles and all that stuff. That will result in an angular acceleration that is proportional to the moment of inertia, or inversely proportional, I suppose. So moment of inertia, if you compare these two, is kind of like a mass. It's like a rotational mass, a rotational inertia. So if you look at mass as the more massive something is, the less it accelerates for a given force. Rotational inertia is the same idea. The more rotational inertia something has, the harder it is to start it spinning or stop it from spinning with a given amount of torque. Okay. Now, in terms of actually calculating moment of inertia, there's kind of two ways. For certain shapes, you can kind of pre-calculate them, and they often have just some sort of coefficient. Yeah, some sort of coefficient. And we'll look at that a little later, but if you look at the units, for the most part, it's going to be some sort of kilograms meters squared. That is the unit of measurement for moment of inertia. If you have a bunch of distinct objects, so like let's say you have trying to think of like, did you guys ever play with like Connects? No. They're basically like you take a bunch of pieces and you connect them with rods, right? So the idea is if you have a variety of pretty much distinct objects that are connected together, like, you know, and you want to know how hard it is to spin this connected body, this connected system, If you take this and you try and spin it, you can take their masses, multiply by the square of their distance from this pivot point, and add them all up. Okay, and we'll practice a couple problems with this. But for now, I'm just kind of writing the equation out so that we can use it for later. This is usually for rotationally symmetric objects like cylinders and spheres and hoops and rings. Not necessarily, I should say usually, but you can essentially kind of come up with something like this for any shape. You kind of can. Okay, and then lastly, you can also talk about a rotational kinetic energy. So if kinetic energy is 1/2 mv squared, you see that rotational kinetic energy is like a 1/2 I omega squared. They really are just transports, or they're very similar. Very similar. Okay, this last thing that I have on the side, when you take an object and you start to spin it, you throw it in the air. For example, if I take this, if my masses are not evenly distributed, this is a very concentrated mass at the end. When you spin it, it doesn't spin around the geometric center, right? It spins kind of like focused more on where it's heavier, where the mass is concentrated. So you can kind of describe a center of mass where it tends to want to spin, right? Where it wants to spin. So if I try and put it at the geometric center, the mass is too concentrated on one side, right? It doesn't work that way. I think what we're accustomed to as the balance point, that is essentially your center of mass. That's where it wants to spin around. And so this is how we calculate it. It's essentially a weighted average. You take the mass of your individual objects, multiply by how far they are away from some reference point, and then divide by the total amount of mass. So it's very much like a weighted average. The more massive something is at a certain position, the more concentrated the center of mass will be towards that position. And then you do it, when you're doing center of mass, you do it kind of like vectors. You do it in the x direction, and then you do it in the y direction. And if you have 3 dimensions, then you do it in the z direction. Okay, questions on connections between linear, rotational stuff, definitions, new terms, meanings? All right. So, let's take a look at a center of mass problem. Say you have 2 objects connected by a massless rod. So 2 spheres. Notice we like to use spheres. Spheres are nice because you can treat them kind of like a point mass. Because they're so, if they're uniform and they're so symmetric, you can kind of treat them like all their mass is concentrated at their center. So you got 2 kilograms here, 1/2 kilogram there. How do we decide where that center of mass is if the rod is 1/2 meter long? So when you calculate center of mass, you need to decide ahead of time where you're going to choose your reference point, your origin, right? Kind of like with torque, you want to choose an origin that is convenient. What makes it convenient is if you know all the distances relative to that origin. So you don't want to pick an origin at some weird spot where you have to recalculate where the distances of all the objects are relative to that origin. If this is 1/2 meter long, I'm just going to pick that as my origin so that I know the other one's 1/2 meter away. And then we calculate. Okay, so to determine the position in the x of the center of mass. I just add up the mass times the distance. Right? So 2 kilograms times its distance, which is 0, if that's my origin, plus this guy, which is half a kilogram, times its distance, which is half a meter, and then divide by my total mass. So it's 0.1 meters from the left. And that should kind of make sense because 2 kilograms is 4/5 of the mass, which means that my center of mass should be weighted 4/5 to the left. Right? Sometimes you will see these kind of questions on the multiple choice section. And if you do it this way, the longhand way, you'll get the right answer, but it may take you a little while, right? You only have about 1 minute and 15 seconds per multiple choice question on the AP exam. That's how it would divide out. So if you can look at this and do it more in terms of ratios, right? Like I said, 2 kilograms is 4/5 of the total mass. So my center of mass should be weighted 4/5 to the left. 0.1 over, or whatever, 0.4 this way over 0.5. That can be a faster way to save time on some of these multiple choice questions. They tend to, on the multiple choice, give you these very convenient numbers. They're not going to give you like 0.87 kilograms and 0.23 kilograms or something. I don't know. Whatever it is. Okay. Student asked me in third period, okay, what if I changed my origin? Would it still work out to be the same? So let's say my origin's on the right-hand side. Exact same problem, but now my origin's on the right-hand side. If you go through the calculations, you'll now get that x is 0.4, which is the same spot, right? Because 0.1 from the left is the same as 0.4 from the right. You should not get different answers or different positions if you change your origin. If you do, you mess something up. The center of mass should end up calculating to be the same spot every single time. Questions about how to calculate this? Center of mass? I think it's pretty straightforward in terms of what the equation is. It is worth noting on the equation sheet that you guys get, I don't think you get this one. Calculating, oh yeah, here it is. That's it. RCM, the position of the center of mass, equals the sum of the individual pieces divided by the total mass. Okay. So there's that one. There are a couple other rotation equations I forgot to bring up that don't show up on here. Okay, so going back real quick, looking at the equations that they don't have any of these. Okay, they don't have any of those. Those are definitions. You see nothing in here talks about alpha or omega. So you need to know that these ones, they don't have all of these either. They actually only have this one. And they don't even say V tangential. So you gotta be careful. You really gotta know what this one is talking about. And if you know this one, the idea is you can figure out the other ones too, because they're very similar. You have the tangential one is equal to the angular one times r, is essentially the idea. They do give you centripetal acceleration. I called it radial acceleration, but they give you centripetal acceleration. They give you torque. Where is it? They give you torque, and also Newton's second law for torque. They even give you kinetic energy for rotation. So they do give you a couple of these. They don't give you this one, but this one isn't really an equation. It's really just recognizing that moments of inertia tend to look like this. Some sort of constant times mass times radius squared. We'll look at that when we get to it. But anyway, so going back, just be mindful about the way they format their equations. may be a little different. So you gotta make sure you know we're looking at this one. That's this. All right, let's look at another example. What if you have 3 objects, okay, distributed in some fashion, okay? So how do we determine the x position of the center of mass or the y position of the center of mass? Pretty much the same thing. Just be mindful that when you're adding the x positions, you're not looking for the distance from the center. You're looking at really the x component. So if I'm looking at the contribution of this mass is 3 kilograms and it's -3. This one is 5 kilograms. It's +3. This one is 8 kilograms, but it's in terms of x position, it's on the y-axis. So it's x is 0. Divided by the total mass, you get something like this. Now the units of this is position. It's a distance. So I ended up just doing this unitless, but this could be meters, feet, inches, doesn't matter. Your answer should match whatever these positions are in distance. Then you do it in the y direction. Again, if this ends up being a multiple choice question, you're trying to do this fast. In terms of the y, right? In terms of the y, if I look at on the y, in the y direction, right? In the y direction, on this row, this 3 meters away from the x-axis, you have 8 kilograms there. On this side, you have 8 kilograms here, right? So in terms of kind of doing like a horizontal line test of like where all your masses are distributed, you have the same amount of mass 3 up as you have mass 3 down. And so that's going to be 0. So you can do that, again, you can kind of try and do that as a weighted average or a quick way to do it. If you see something like this and you do a vertical kind of a line test and you see where your masses are distributed and you have different masses all over the place, I would suggest just doing the math. But if you see something like this where you can kind of quickly determine, well, you have 8 down here and 8 up here, that's going to be 0. That can be another way where if you're very familiar with it, you can you add more time, get more time. So your center of mass is going to be somewhere around here. Now sometimes you'll see the symbol for center of mass is a circle with an X in it. Sometimes you'll see this in like aeronautics books for airplanes. You're trying to find the center of mass of an airplane, which matters a lot because that's where it tends to pivot when you're flying through the air. Okay. That's pretty much it. That's how you calculate center of mass for discrete particles, objects. What if you don't have a discrete object? What if you have something like a bar and you have a bunch of, and you're trying to figure out where the center of mass is for this bar? You now have a distributed mass, right? Now maybe it's uniform, maybe it's not, but what you need to do is you need to convert this into into the calculus version. You need to add it up over all the little slices that you can create. So instead of having distinct particles, it's kind of like how do you take a bar or a solid object and chop it up into distinct particles? Well, before we do it as in the calculus method, think of it like this. Let's just take one slice, one not infinitesimally small, but like an actual significant slice, delta m. It is important to note that you don't take a slice of delta x. You're taking a slice of delta m because your weighted average is your mass some position away from your origin, right? Whatever your origin is, right? So it's not really a delta x. We'll come back to delta x. This delta m is some position x away, right? The problem with this is when we end up getting to the calculus and we start trying to add up all these little slices of mass, it's really hard to integrate with respect to slices of mass. Usually when we do integrals or we try and add things up, I'll leave this here. Let you try and figure out what that's saying. When we try to integrate, we like to try and integrate in spatial directions. Like, how far is it? Is it a dx? Sometimes we integrate with respect to time, dt. But what does it really mean to integrate with respect to dm? How do you add up a bunch of little masses? It's really hard to do. So instead what we do is we want to try and look at, well, how much of this bar does this much mass take up? If I convert this delta m into a delta x, I can figure out, in other words, let's say I have a 1 kilogram bar, and I'm looking at a 0.1 kilogram chunk of that bar, a tenth of the mass. You would assume, if it's uniformly distributed, if it's a tenth of the bar in mass, it should be a tenth of the bar in length, right? I think that's very reasonable. So if we can convert it into how we're chopping up the positions and translate the mass slices into positional slices, then we can add them up. It becomes a lot easier to add it up. And so sometimes you'll be given what's called a linear mass density. Maybe they'll give you a surface mass density or a volume mass density. In other words, a volume mass density is your typical density, right? Density of water, 1 kilogram per cubic meter, or whatever, that kind of thing. Wait, is that right? For water? I forget. Anyway. So if you look at linear mass density, what does it really represent? It's kind of like how much mass do you have per slice, right? That's essentially what we're looking at in terms of linear mass density. So there's a couple of ways you can write it. Lambda is like this, or delta x is equal to this, or you can algebraically rearrange it, but this is really the main idea. Your linear mass density is how much mass you have in each slice. Right? If it's uniform, this should be true everywhere. Like 1 kilogram per 1 meter is the same as 0.1 kilograms per 0.1 meter, so on and so forth, right? So if we take this and translate it into calculus language, this is essentially the same thing. Right? A slice of x is equal to 1 over my linear mass density times a slice of mass, or my slice of mass equals to my linear mass density times my slice of x. Same thing. You'll notice I put lambda x because in this case we're kind of ignoring how it's distributed top down. We're just looking at how the mass is distributed from left to right. But you could have a scenario where it's thick, it has thickness this way and thickness this way, and then you have to think about how it's distributed up and down and how it's distributed left and right. You can split them up, right? How is my mass distributed left and right? That's my x. How is my mass distributed up and down? That's my y. And then if you have 3 dimensions, but you probably won't run into any 3-dimensional stuff, you have that. So when you substitute, what happens is we can now convert this dm, which was originally a slice of mass, into a slice of position, a slice of thickness, which is much more useful because now I have position and slices of position. Whoops. Right? And now you have matching variables, which makes it a lot easier to integrate. It's really hard to look at x as a function of mass. It's much easier to look at x as a function of x. And then you add it all up. So in terms of interpreting what this is saying, it's compare that to what we had before. Okay, and again, as you guys take this class, I'm really hoping that taking this class and looking at the applications of the calculus can help you understand the calculus a little better. This integral is effectively the same as just adding it all up. right? This integral of x dm is the same as summing r times mass. R times mass. Position times mass. But you're just looking at really small pieces of that. The 1 over big M, that's the total mass. If you're wondering what this big M is, it's the total mass, right? So, but the integral part, that's this sum. All we're doing here from jumping from this to this is we're saying we don't want slices of mass, we want slices of position. Okay, so we will come back to solving this using calculus later. But what I want you to understand here is that it's saying the same thing. Some things to be careful about is you have to choose ahead of time where your origin is. Is it going to be here? Is it going to be here? Is it going to be here? Because that's going to determine what x is. X is the position of that slice. That's x. X is the position of that slice. Delta x is the thickness of that slice. So in the same way, dm or dx is the thickness of that slice. X is the position of that slice. How far is it from your origin? And you add it all up. When you add it all up, this is usually not an indefinite integral. What I mean by that is there's usually limits of integration. You're actually adding it up from one side to another side. And then we can go through the technique for determining that a little later on. Don't worry about the nitty-gritty details. Okay, so most of the time, you'll probably deal with something like this, discrete particles. I have seen in the last like 10 AP free response problems, calculating this by hand, a integral kind of problem, maybe once or twice. I'm not saying you shouldn't know how to do it. I'm just saying worst case scenario, if you need to cut your losses and you need to study something, just know at least this much. And then you could probably do fine. Right? This is like extra. Okay. Any questions about center mass? Or just kind of cursory understanding of what happens when you start having a continuous body? Or continuous distribution? All right. So the next thing we need to talk about then is moment of inertia. So center of mass is where an object tends to want to rotate. And once it does start to rotate, how easy is it to make it rotate? That's what moment of inertia tells you. The higher this number is, the more torque you have to apply to get it to start to accelerate. So let's look at that one problem that we were doing, calculating the center of mass. The one where we figured out the center of mass is 0.1 meters from the left. If you calculate its moment of inertia, this object has a mass of 2 kilograms times 0.1 meters from the center mass. This one is 0.5 kilograms. It's 0.4 centimeters from the center mass. Notice that because it's squared, you'll never end up with some sort of negative center of mass. That wouldn't really make any sense. And when you get it all, add it all together, you get something like this: 0.1 kilograms square meters. So if you look at how it fits into Newton's second law for rotation, it acts kind of like this. Since the center, the moment of inertia is 0.1 kilogram meter squared, 0.1 newtons meters, that much torque, will accelerate that much inertia 1 radian per square second. The same way, if you had 0.1 newtons, it would accelerate 0.1 kilograms 1 meter per square second. It's the same kind of, like visually, how you think about pushing, pulling something, speeding it up. How does mass play into that? Apply it the exact same way for spinning, for turning. Right? How easy is it to spin something? Okay. Something I want to point out, this distance, the r, unlike center of mass, this is the straight line distance, the actual distance of the object from the center. So if you look at this diagram, it's not, you're not splitting it into x and y for moment of inertia. It is the actual distance away. Yeah, don't worry about the velocities for now, but the actual distance away and the amount of mass at that point, so that you get moment of inertia like this. And you add them all up. Add them all up. Okay. So, for example, you look at this problem. You have this, and it's spinning like this, right? This is the pivot. It's worth noting that when you talk about moment of inertia, you wouldn't talk about the moment of inertia of an object. You talk about the moment of inertia of an object spinning around a certain point. You have to designate where it's spinning around. The moment of inertia of this system is different when it's spinning around here than if it's spinning around here, than if it's spinning around here, or here, or here, or if you took it and you threw it up, then it would then spin around its center of mass. Its moment of inertia is different every single time. Okay, it really depends on, because it's based on r. And r is the distance from the pivot, right? When you're calculating center of mass, this is different. This r is the distance from some arbitrary origin. You can choose that anywhere, and you get the same answer if you use different origins. You should end up having the same position for your center of mass. This is different. This r is the distance from the pivot, and so it depends on where it's spinning around. And so you can kind of look at how they're calculating their moment of inertia for this guy, right? You have this straight line distance, the 8 centimeters, and this straight line, this straight line distance is 6 centimeters, and then you get nothing from the object right at the pivot, and you get this moment of inertia. Okay. Any questions about what moment of inertia is, or how to calculate it for individual objects? So if you look at the equation sheet, it gives you two. This is the distinct particle version. This one is the calculus version, meaning if you have a continuous body, a distribution of mass. So, for example, again, if you look at the rod, so this is a pretty good example. This is on page 320, right? If you have a rod, how do you determine this, the moment of inertia as this spins around this pivot on the left? You're going to have to do something very similar. You need to convert that little slice of mass into a slice of position. You see the dm turns into a dx, and they introduce this linear mass density ratio, mass over length, and then they calculate from there. Yeah, we'll get to this part later, but just look at how they're first setting up the problem, right? Okay. So, a couple things, important things that you need to know about moment of inertia. If you look at the equation, it's mass times r squared. So, with center of mass, you can have negative positions and positive positions, which means they can cancel out, and that's how you have like a center of mass like in the center or something like that. Moment of inertia is all positive. Any mass that you throw on there, somewhere that's displaced from, or that's far from, or not far, but not at the center, is going to contribute to its moment of inertia. It's r squared. So that means that the further away it is, it actually increases the moment of inertia at a quadratic rate as opposed to the mass. So if I have an object that is heavy, that may not have as much moment of inertia as something that's light, but has everything pushed out to the sides. So if you look at the moments of inertia of a variety of objects, let's look at this. Okay, so if you look at this set of objects and their moments of inertia, I want you to take a look at where is it the greatest, which shape has the greatest, which shape has the least between flat, whatever these flat objects and round objects. What tends to have the most moment of inertia? What do you think? Which one's the most, which one's the least? Can you guys see these numbers? Right. If you're looking through, this is kind of what I was talking about earlier, where I had this C mr squared. It's kind of like this coefficient that is a measure that's based on the shape. Yeah, it's based on the shape. By the way, this rotation of this solid sphere about a diameter, it's like if you take a sphere and you're just spinning it, you're not just rotating it in all directions, right? You can only really spin it in one direction, which is, like this. That's 2/5. This one is just a straight mr squared. This is actually a kind of an interesting result, because that means that if you take a cylindrical hoop like this has the same moment of inertia as if I took all the mass, crumpled it up into a little ball, and swung it on a sling with this radius. It's the same moment of inertia. In other words, it takes as much torque to spin that sling with that much mass as this takes to rotate this one. Because it doesn't matter that the mass is distributed around the hoop. The point is that every single element of mass is a distance r from the center, right? It's all at an r from the center. So it's no different than if I just focused all of it on one object and slung it around. This is 2/5. Which is the least. Notice that the solid sphere has less moment of inertia than the spherical shell, because the spherical shell pushes all the mass towards the edge, right? It's a shell, so it's thin. All the mass is concentrated on the edge, as opposed to being distributed. That means some of the mass is closer towards the center, and so you actually have less moment of inertia there. In other words, this is easier to spin than this one. This is easier to spin than this disc, the solid disc, which is easier to spin than the shell, which is easier to spin than the hoop. So if on the AP exam they give you some weird shape, two odd shapes, like I take let's say I take something like this, and I spin it around here. And I asked you, which one is easier to spin, this one or this one that is a shell? Right? Generally speaking, this one should be easier to spin because the mass is not as concentrated on the outside. If it's distributed versus concentrated on the edge. This one's easier to spin. A couple interesting consequences about things that are easier to spin. For example, if I take these two of equal mass, this is where I'm going to need your desk. So I apply this it's the same radius, right? It's the same radius. But this one's just solid, this one is a hoop. And so the same mass, gravity will pull on them the same, they'll have the same torque on them to make them speed up. Camille here is going to catch these. So which one do you think, if I let it roll down, we'll get to the bottom first? The solid one, why? Okay, so its moment of inertia is lower. Why does that mean it should be able to travel faster?
It means that the rotational energy, like it'll need less rotational energy.
It'll need less rotational energy. Pretty much. Kapil?
Didn't Galileo test that or something like, doesn't matter what the mass is, they'll just fall at the same rate?
That was a little different. He did a similar experiment, but he had to use the same shape objects. These are, I know they're both cylindrical, but these would be considered different shapes. Like if I drop them, yeah, they accelerate the same rate, but rolling is different. Okay, rolling is different. And kind of like what Celine was saying, if this has a lower moment of inertia, there's a little more to it, but if we look at rotational kinetic energy, this I omega squared, we'll go through the math of how to demonstrate that the rotational energy is less on this one. But you can also kind of relate it to, where's that equation? You can also kind of relate it to this, that if you have the same torque and you have less moment of inertia, you should have greater angular acceleration. You should rotate faster. All right. Ready? So not only is it spin faster, I mean, you can tell it takes less to get it going. That's the main idea, right? It takes less to get it going. It's less moment inertia, it takes less to make it spin than this one. What if they're different sizes? What if they're like different mass, different radius? So what if I had a ball and then like a way bigger ball? Like this guy. So these have essentially the same shape though, right? They have the same shape. They're both essentially solid spheres. And so then we'll go through and we'll show it, but the idea is, kind of goes back to what Selena was saying about energy. They will both transform that gravitational potential energy into kinetic and rotational, translational kinetic and rotational kinetic energy the same way, because they have the same shape. Don't worry about this one. Yeah. Right? It's pretty much about the same. Or I can put the little ball in front of you guys can see. It's pretty much the same. The shape determines how it's converting that gravitational potential energy as it goes down into rotation and translation. The same, similar. Okay, so on the AP exam, if you ever get this question on, what does moment of inertia influence? That's it. How easy is it to make it spin? Any questions on moment of inertia? I mean, I know we didn't do too many calculations, but at least any questions about that calculation? If you have discrete points? I think we're going to come back to revisit the calculus a little later. I don't want to do it yet. Okay, so let's actually look at the rotational kinetic energy and how to calculate off of that then. Let's see. So, actually, let me go to here. Okay. One thing you need to know about rolling motion, specifically about rolling motion, for rolling motion. Okay. There's a particular condition that we often look for rolling motion, as if there is no slip. Okay, if it doesn't slip, in other words, if I take this and it's rolling and not sliding, you know what I mean? So sliding would be like this. It can roll and slide, but if it is just rolling, there's a very specific connection between its translational velocity and its angular velocity, which is this. This is only true, the translation, let me not write it like that, sorry. Let me say it like this, VCM, the velocity of the center of mass. The velocity of the center of mass is equal to omega r only if there's no slip. No slip. If it starts to slip, it's really hard to know how fast it's spinning and how fast it's moving translationally. If it's not slipping, then this relationship is exactly true. And again, I'm going to skip the derivation of it. You just need to know that that's true. If this is true, okay, let's look at an object that is spinning. Right? What is the kinetic energy of this object that is rotating? What we end up seeing is that it splits into two parts. There is a rotational kinetic energy part and a translational kinetic energy part. Okay, let's look at how we can apply this. I'll leave this up for just a second. Notice that this has to be the moment of inertia about the center of mass. And then omega is how fast it's spinning. Okay, let's say you have this object like a disk that is rolling down a ramp with angle theta, and it starts to height h up. And we want to know, by the time it gets to the bottom, how fast is it going? If it were just a box that was sliding with no friction or something like that, then we can say it'd be like free fall. You have mgh equals 1/2 mv squared, something like that. But in this case, you now have to take into account that it's rotating. Some of this energy of the mgh goes into rotating it. Sorry, that's the cm. If you can't tell what that says. I around the center of mass, omega squared, plus 1/2 m, mv cm squared. Okay, the velocity of center of mass, and that's it. Okay. So, but we have a relationship. If it is not slipping, there's a connection between how fast it can rotate and how fast it can translate. So we actually substitute that in for here. You get mgh equals to 1/2 ICM VCM over R squared plus 1/2 MVCM squared. Right? So what is I? I is the moment of inertia of this object. Instead of saying for a particular disk, as we saw, the moment of inertia is usually some sort of coefficient times mr squared, right? It's usually something like that. Here I want to stay consistent with the book, so I'm going to use a capital R. I'm going to use a capital R. Okay. So take a look at what happens. The R squareds are going to cancel out. The masses can cancel out. So actually this GH, and actually this half, I'm going to multiply both sides by 2. Get rid of that half. So you're going to get like a C plus 1 VCM squared. You guys see that? The way that algebraically works out. These R's cancel. They both have a VCM squared. I multiply both sides by 2 to get rid of the half. So it's like a C plus a 1. Or the velocity by the time it gets to the bottom is equal to the square root 2gh over c plus 1. So in other words, that coefficient, which determines its moment of inertia, ranges from 0 to 1, right? At the most, it will be C can be 1. That's the most it can get. That is if you have all your mass concentrated on the outside of this object and it's rotating like a hoop. You can't really get anything more than that. You can't like have it push extra far from R. The simplest case when C is 0 is when you have a particle with no volume whatsoever. That is like our box case. The case when the box just slides straight down with no friction, a particle. So when C is 0, you get the traditional square root of 2gh. We've seen that before. Square root of 2gh gives you the velocity of free fall, pretty much. So what does rotating do? At most, it can take away this extra amount of energy, right? So if C becomes 1, you have the square root of, so VCM is anywhere from square root of GH, or sorry, square root of 2GH greater than square root of GH. At worst, it's square root of GH. At best, it's square root of 2GH. So it's not like any answer is possible. There is a range, but what you can see then is if it's not slipping, at worst you lose about what, square root of 2, 1.44, or you go from square root of GH to an extra 41% of that in terms of how fast you can go. Anyway, so this is kind of how some of the calculations sometimes end up working out. What you need to do now when you do energy, you need to take into account that some of that energy can go into rotation. Yep.
How will you be able to determine whether there's slippage or not?
It will tell you. Yeah, it will usually tell you. If there is slipping, usually then it should still tell you how fast it's going. So for example, there was an AP problem like this where it said it's slipping as it's rolling sliding through some distance, and it would tell you, okay, it traveled that distance in 10 seconds. So if you know how far it traveled, then you can figure out what its translational velocity is. I think from the friction, you can figure out how much energy is lost or something like that, and try to figure out some of the other parts. I can't remember exactly how the problem is set up, but it will tell you some additional information for you to figure it out. Okay. Questions about rotational energy. So all it's doing is you just now have to take into account that it can spin, and there's energy there. That's really all it is. Okay. Since we have time, we can actually get through one of the last parts of this, which is angular momentum. Okay, so actually I didn't include that on this list. We can go back and include it on this list. So if momentum, I ran out of space, if you still have space, if momentum was P equals mv, what do you think angular momentum will be? That's it. So, I'm going to put this on here too. Sometimes you will see this. Technically, momentum is a vector, right? So angular momentum will also be a vector. Its vector is in the direction of the where it's spinning, right? So if you have positive angular velocity, it has that direction of angular momentum pointing out at you. You can talk about the angular momentum of a particle that is spinning around a spot, which will be r cross p. Let's not worry about this one too much for now. Let's look at just I omega. Actually, let me go back. Sorry, let me go back real quick. So we also said with momentum that your force is like a change in momentum over a change in time, right? So actually, a torque is also a change in angular momentum over a change in time. You can say that too. That's a vector, that's a vector. So this is a vector. So change in a force is a change in momentum or a change in time. So all the stuff that we talk about with impulse, you can kind of talk about like an angular impulse and stuff like that too. Okay. So if we look at angular momentum, is this L equals to I omega. Okay. But I is a function of your radius, right? It's usually some sort of, mr squared, some cmr squared, right? So as you change the radius of an object, if you change the radius without an external force, then, in other words, if you apply kind of conservation of angular momentum, then changing your angular momentum will necessarily change your velocity, your angular velocity. It's kind of like, well, let's look at a linear case first, and then we'll draw parallels. P equals mv. This means that, you know how in some movies with like in space or like on a boat, they're like, oh, we're not going fast enough. We need to drop cargo so we can go faster, right? It's like if you lower this, you can increase that. It's kind of the same thing with angular momentum. Except that instead of having to drop your mass, you can lower your angular momentum by just getting smaller, right? So that is this thing. Right? We all know, we're all used to this one. This thing, right? Where you start with high angular momentum, or not high angular momentum, moment of inertia, and then you have little moment of inertia. Actually, I remember doing this at Westview. We used to have these rolly chairs in the clusters. One time what I did was I laid flat like this, and then I tucked in, and the chair was just like, it's too much. It's too much. But I think we're all pretty familiar with that, right? It's the ice skating effect. You change your radius, and then you get angular momentum. There are some other really crazy things that happen with angular momentum. And how torque affects angular momentum. So, if a torque leads to a change in angular momentum, I want you guys to think about for a second which direction the torque is applied from gravity when I let this go. Okay. Which direction is the torque? Towards you guys, right? Yeah. The torque is towards you guys. Yeah, do that. Do the right hand rule. The force is down, but the lever arm, R, is this way. So R cross F, your torque is towards you. Torque is a vector. That means the torque vector is towards you, which means that the angular momentum change of this system is towards you. It will try and spin like this. So what happens if I give it an initial angular momentum this way? It already has angular momentum to the right. So it can't fall. Yeah, it was Mike. I think Mike put a thing about this from Veracity. So it seems super trivial because if it's not spinning, right, it can just fall. What ends up happening is, again, if I spin it towards you, okay, what direction is the angular momentum? This way. Right? This way. So take your thumb, right? The torque is towards that way. Your angular momentum is this way, so it wants to do this. Right? Your angular momentum vector is going like this. But by the time it gets to here, now where's the torque? The torque is that way. So it wants to go like this. And as it keeps spinning, because it keeps trying to rotate like that, the torque is constantly causing it to spin. Okay. It's kind of sometimes, so that is like the angular momentum explanation. It wants to spin like that. Sometimes I forget which direction it wants to precess. This is called a gyroscopic precession. So I think of it like, if I spin this towards you, the wheel will look like it's trying to moonwalk. Right? It goes, does that, I don't know if that makes sense. Right? It's trying to spin like this, but it's walking backwards. It's not rolling forwards. It's moonwalking. I don't know. That, for some reason, that sticks for me. That sticks for me. If that doesn't stick for you, just use a different method. But if it's spinning towards, it's spinning this way, you would think it wants to roll that way, but it goes the other direction. The moon walks. That makes sense. Okay, so let's combine. So I start this spinning. I'm going to give it a certain angular momentum. Okay. If I try and change, well, actually, here I'm going to spin it like this. Okay, so right now it has an angular momentum downward. So, right. See how it was doing to me? Why am I turning when I'm turning this? Why am I turning when I'm turning this? Right? What law says that I should turn when this turns? Conservation of angular momentum. If it already had angular momentum downward, internally as a system, I now turned its angular momentum the other direction, so I need to adjust. I'll adjust accordingly. It's kind of like if you, let's see, yeah, I can't think of. It's really hard to jump in the air and then suddenly turn, right? If you jump in the air, you try to turn the bottom part of your body goes the other direction. It's the same idea. You can't ever just suddenly twist everything in the system in one direction. If you twist, you go in opposite directions. There's actually a really good video on this about how cats always land on their feet and how they do that. We will watch it next time because we only got about 4 minutes left. But yeah, so we'll look at all the math behind all that, that crazy wizardry. But it all falls under this kind of rotation stuff.